In this lecture, we're going to cover part of section 6-12 on modulation. Here we apply the Fourier transform and Fourier series properties that we've learned elsewhere in the class to prepare signals to be transmitted, whether that be over the air, over a wire, over an optical cable, or some other medium. For the electrical engineers, you will be taking a class called EE3032, Principles of Communications, where you will look into these modulation techniques in a lot more detail, and you'll look at a variety of them. But first of all, let's look at the problem that we're trying to solve. If we look at the Fourier transform, and I'm going to draw a magnitude Fourier transform here, and I'm going to draw it as a function of frequency f in hertz, which is traditional for when we're talking about audio signals, and it's also traditional when we're talking about wireless or wired transmission medium bandwidth. So here we have frequency in hertz. We just need to divide out 2 pi from the omega frequency. Now, if we look at a typical human voice, most of the energy is below about 3 or 3.4 kilohertz. So when we do the Fourier transform of a human voice, we might see a lot of energy here, and especially at lower frequencies. And there may be some energy above 3.4 kilohertz, but that we choose some band limit at which we're going to say we're going to filter out or remove that. Now, for very high quality audio, we might set a much higher limit than this 3.4. So when you're listening to a music recording over a high quality streaming service, we might use a higher limit. But the point is, there is some limit over which we filter out and say the signal will not have any more frequency components in the Fourier transform that we need to transmit wirelessly. Now, since our audio signal for our example here, and most signals of interest that we want to transmit are real value signals, we know that the Fourier transform has conjugate symmetry. So that means that the magnitude Fourier spectrum is going to have even symmetry. We have the same magnitude at positive and negative frequencies. So here we draw this to look like a mirror image. And let's call this voice number 1. And then there's also a phase spectrum, but we're not drawing that here. So there might be several voices that we want to transmit, or several audio signals. Let me draw one here and call it X2. Here is going to be a low fidelity musical signal. So this one over some time might have some peaks where various instruments are playing, and we have the same frequency access as we do above in this example. And this again, I'm showing it here without low frequencies, but it might have the low frequencies. But again, the magnitude spectrum is going to have even symmetry. Now, here is the point of modulation. When I transmit this signal over most media, I am not able to use these low frequencies down to DC and up to low frequencies such as 3.4 kilohertz. You know, on Wi-Fi, we're talking about signals being transmitted at frequencies around 2.4 or 5 gigahertz typically. And if we're talking about radio transmission, we are usually in the high kilohertz to low megahertz range for radio transmissions. So we need some way to modulate or take a signal and move it up to the higher frequencies. So we call these signals here on the left, shown in the Fourier domain, baseband signals. They exist from 0 hertz up to some frequency, and then there's also the mirror image at the negative frequencies. So what we're going to do with the modulation techniques we look at is somehow move these signals to higher frequencies. So one technique that we're going to focus on in this section says we have some high frequency that our medium can support, called a carrier frequency. For radio, this might be, as I said, in the high kilohertz or low megahertz range. If we're using the ISM bands that 2.4 gigahertz Wi-Fi works in, this might be somewhere around 2.4 gigahertz. And we take that Fourier domain signal and we move it up so that it is centered not at 0, but at this high frequency. And the frequency axis, of course, is compressed, but here I would have FC plus 3.4 kilohertz, and on the left I would have FC minus 3.4 kilohertz. And since we are dealing with real signals, typically there is going to be a mirror image around negative carrier frequency. There will be, and it is going to look like that. So that is what happens when we add in, when we modulate X1. Now let me take X2 and do this. What if I put another carrier frequency slightly below the first, so let's call this FC2, and I take X2 and I move it up to that frequency. So I have this spectrum here, and minus FC2 here, and we're going to have the mirror image. So as long as these do not overlap, they can share the bandwidth, they can share the wireless spectrum and be transmitted together. So this is one of the simplest forms of sharing multiple radio signals. This could be done over an optical fiber. It could be done over a wired connection as well. So we're going to look and take a brief introduction at a couple methods of increasing the frequency, but not otherwise disturbing the structure of a signal. On the receiving side, then there are also techniques to move the frequency back down and get us to the original baseband signal. So in order to design circuits to do this, we need to understand where the frequency content of our signal is, and the Fourier transform and also the Fourier series are going to help us look at signals that way so that we can share the bandwidth of whatever medium that we are transmitting one or more of those signals over. The simplest approach to transmitting, moving a signal up or modulating it to a higher frequency is called switching modulation. The circuit to implement this is very simple because all we do is we take a modulating signal, xm of t, and it is a wave that alternates between 0 and 1 volts. And here I'm showing it as a 50% duty cycle square wave. And it has a frequency that we run at. So here we have time over 2 minus time over 2. And there is an frequency that corresponds to the time of that waveform. And it'll have amplitude A, or we could consider it 1 volt for our example. So if we go back to chapter 5 and look at table 5.4, this is a periodic signal, so it has a Fourier series. And it has a DC offset, so we can see the average DC value. The DC value is half a volt because half the time it's at 0 volts, half the time it's at 1 volt. We've drawn it here to be an even signal, so when I write this out, I'm only going to have cosines with no phase shift. And it turns out that if we look at that, we have 2 over pi at the fundamental frequency. So I'm going from, I need omega here, so I take f and I multiply it by 2 pi to get omega. And then we have only odd harmonics for this. So 2 over 3 pi, and the next one will be plus 2 over 5 pi, and so on. But here we are at the third harmonic, so it's 2 pi times 3, the carrier frequency, times t, and then we will go on from there. So that is that is the square wave based on the Fourier series. Now, if I let my signal to be transmitted be x of t, and I multiply x of t by the square wave, I could express it a couple different ways. I could say it's 0 when the square wave is inactive, and it's x of t when the square wave is active. So that would be a piecewise definition like we used earlier in the class. But to show how the switching modulation works, it's going to be more useful to multiply the terms of this Fourier series expansion out. So my transmitted signal is going to be the product of the message, or x of t, and the modulating signal, x of m, which is the square wave, but we're going to look at it in terms of the Fourier series. So now I'm just going to take x of t and multiply it by each term of the Fourier series. So we're going to have a half of x of t, and we're going to have 2 over pi scaling up x of t, but multiplied, and this is where the term modulation comes from. When we multiply by a sinusoid, that is a basic form of modulation. And then the series goes on from there. We have 2 over 3 pi at the third harmonic, because we just have odd harmonics in this square wave. And this is at 3 times the fundamental frequency. So 2 pi, 3 fc t, and we go on from there. So now if we do the Fourier transform of this non-periodic signal, because now we've multiplied it with the presumably non-periodic voice or other audio signal that we want to send, and we do the Fourier transform, we can apply the linearity and scaling properties of the Fourier transform to take the Fourier transform of this signal and the Fourier transform of this signal and the Fourier transform of this signal. We can consider all those Fourier transforms separately and then add the results back together. And let's do a graph of the magnitude spectrum of y here. So I have y, which is my modulated signal, my signal that is switched on and off, and I have some interesting things happening here. We can see with the cosines at f of c and 3 f of c, and we're also going to, since this is a real signal, have the negative frequencies. Now, what we have is our original signal, x, is going to have, when I take its Fourier transform, it's going to have some shape to it. Let's just assume it's something simple like that. And it goes up to some bandwidth frequency b here. So now we can see that we have in our transmitted signal, we have half of the original signal. So we're going to have this original Fourier transform spectrum moved up here, but it's going to be cut down by half. Let's assume that it fits in like this. So I'm assuming that the bandwidth B is relatively small compared to the carrier frequency C. And this is a condition in order for this to work. So the specific condition is the bandwidth is going to have to be less than half of the carrier frequency, and it might be a lot less than that because we don't want overlaps as we add these together. Now let's look what happens here. I take x of t and I multiply it by the cosine. But remember from chapter 5, the cosine, when I take its Fourier transform, it has impulses at plus and minus, or minus and plus, its frequency, which is fc. I'm writing this here in terms of frequency in hertz. You could also do it in radians per second omega. So that's the Fourier transform for that. And when I multiply that by another signal, as we showed back a couple days ago in chapter 5, I take whatever the spectrum of this x of t was, and I move it up to plus fc and minus fc. That is the effect of multiplying by this cosine. That was called the modulation property when we went through properties of the Fourier transform. And I see here I had a height of 0.5, here I have 2 over pi. We end up getting actually 1/2 at both the plus and the minus, so I have 1 over pi. I have a smaller amplitude, but I have a copy of that spectrum of x at plus fc and minus fc. And I'm going to have another one at 3 fc, but now it's going to be only 1/3 the height of this last one because there's that 3 in the denominator there. So I have this. So what we do, after we create this signal, we then run it through a filter that blocks the low frequencies that are below about fc over 2, and it also blocks the higher frequencies that are above fc over 2 plus, that are above fc plus the bandwidth. So we need to go at least from fc here to the bandwidth, and we might go as high as fc plus fc over 2, which is halfway to that next one. Or we could even go further because nothing happens at 2f of c. But in any case, we need a band pass filter that keeps this signal right here. And it'll also keep that one. Since we're going to have a real signal, it will have positive and negative. Now, what that gives us is it has done exactly our modulation. Our modulation property says we don't need the original signal. We don't need these things at higher frequencies like plus or minus 3 fc, but we do want one at fc, this higher frequency, to transmit it on. This approach has the benefit of being very simple to implement because all we did was we multiplied by a signal that was 0 or times 1. So we switched, or we turned x of t on and off, but we had to have an fc that was large enough in order for this to work. So this won't work if we choose f of c to be too small. But once we did that, all we needed to do was to ground the output for half the time and let the output be equal to the signal we're trying to transmit for the other half of the time, and switch back and forth. Very easy to implement that circuit. Then we do a filter that blocks the low frequencies and blocks the high frequencies. It just keeps a range of frequencies around fc, which is called the carrier frequency, because it carries the signal. And we have a way to transmit our data on a medium that can only handle the higher frequencies around fc.